Okay. Today we are going to present our project about exploration of modularizing domain prior with adapters in biomedical text mining. Our group member contains Han Si Yang, Renjie Pi, Fating Hong, and Ji Peng Zhang. So let's begin. Yeah. So here is the outline of our presentation. Let me first begin with the motivation and proposal part. Okay. Yeah. It is well known that the most effective way to achieve state-of-the-art performance for natural language tasks is to fine-tuning or continue pre-training a pre-trained language model. When it comes to a new requirements to new domains, all you need to do is just continue pre-training or fine-tuning birth parameter in the domain-specific data sets. Yeah. So what's the price? Firstly, continual pre-training or fine-tuning is very expensive and time-consuming. Suppose that we have every year's news documents that we want to train the bird on them. We will have to keep training checkpoint endlessly. So as previous work shows, for example, in order to fine-tuning the bird on biomedical domain, like we want to get a biobird, we may need to train 23 days on a machine with 8 NVIDIA V100 GPUs. Yeah, and the second price is that fine-tuning or continual pre-training paradigm makes bird less extensible, since domain-specific training will result in catastrophic forgetting. Yeah. Let us first look at so here comes our proposal. Before I present our formal proposals, let us first take a look at the adapter training. So what's the adapter training? Instead of heavily tuning full parameter of bird, we can add an extra adapter module to constrain the parameters update in this extra part while freezing the giant backbone model, just like the figure shows. Yeah. Based on the adapter techniques, we propose our idea for this project. Here, we propose to modularize domain priority into adapter modules. The reasons are like this. First, adapter has great extensibility. That's to say, it can help avoiding catastrophic forgetting by freezing backbone model. Secondly, backbone model achieve various functions by just adding corresponding adapters, which means it is easy to be plugged in various domains. Yeah, that's all.
I am Fating Hong. I will give a quick talk for the part of background and related work. The first part is transformer. Here we first recap several basic components in self-attention network proposed in transformer, which has shown impressive results in various natural language projection tasks. The self-attention computation module in transformer, there is the scale dot product attention can model pairwise relevance by calculating attention weights between pairs of elements of an input sequence. Its output can be computed by the equation as shown in the slides. Always, multi-head attention is used to allow the model to generally attend to information from different representation subspace at different positions. And another background is about adapter tuning. In the rest part, we will introduce a specific parameter efficient tuning method named adapter. It will be widely applied in our experiments and approach. Thus, I just give a brief introduction about adapter. Adapter approach insert a small module between transformer sublayers. The adapter layer is generally composed by a down projection layer to project the input feature to a low dimension representation space, and following activation function F, and then an up projection layer to map the intermediary feature back to original dimension. Besides, a residual connection is applied with this bottleneck architecture. We can represent it as the equation like this. And about the relative work, here we mainly investigate two types of relative works. The first one is domain-specific training. Usually, pre-trained language models can achieve confound performance improvement by just doing continued pre-training in large domain-specific corpus. Later, pre-trained language models can achieve much higher performance by training from those domain-specific module checkpoints. There are several famous domain-specific pre-trained language models in recent years, like BioBirds, XCI5, XCI-Birds, and so on. And the second type of relative work is parameter-efficient tuning. We know that fine-tuning from those domain-specific checkpoints are both time-consuming and it will result in higher costs. Researchers attempt to search for efficient ship tuning methods. Many parameter-efficient tuning methods are proposed in recent years, like bit fit, default method, adapter methods. For example, the bit fit frees most of the transformer encoder parameters and turn only bias turns and the task specific classification layer. And more details about these relative works are reported in our reports.
Hello, I'm Hans Yang, and I'm going to introduce our method used here. I'm going to introduce the data-specific adapter. So we further introduce how adapters are used for different data sets. The general idea is simple, as is shown in the illustrative figure. We'll add the adapter module to the transformer model, and the parameters of these adapters are trained on each data set, as here we have 4 data sets and corresponding 4 adapters. Therefore, we can encode priors from the specific data set into our model. Mathematically, it corresponds to the following optimization problem, with theta denoting the transformer parameters which are kept fixed, and phi denoting the adapter parameters to be optimized. Okay, now we are going to introduce domain-aware adapter fusion. So note that different data sets can belong to different domains. For example, data about drug, data about genes, data about proteins. Motivated by the similarities between different data sets, we propose to fuse the adapters that are trained on these data sets belonging to the same domain. The general procedure is also shown in this figure. So here we still have many different data sets, but they are now belonging to the same domain. And as is introduced previously, we will train different adapters for these different data sets, as is shown here. Then after these adapters are trained, we will do a fusion training over all these adapters to help better encode priors for this specific domain. So also take a look at these equations. So the first part here, the adapter training is the same as in previous slides, but here we have different adapters. And then after all these adapters are trained, we'll here apply a new parameter that is also called phi-m. This refers to the parameters for the domain adapter fusion part. And here we kept zeta fixed, phi1 to phi-l all fixed as is. They are all trained from this data set. Okay, so as for our detailed implementations, we use the BioBird pre-trained checkpoint provided by their original repo on the GitHub. And we compare different methods on the NER, or also called named entity recognition task, in the biological domain. Some details and statistics about these data sets are shown in the table here. And during our experiments, we always use the F1 score as the performance metric.
Here we give some analysis of experiment results and some discussion. In the experiment section, we aim to derive the answers to these questions. First, can adapter tuning and domain adapter achieve comparable results with fine tuning? And second, can pre-trained domain adapters be inserted into any backbone model with just fusion training? And third, how do the domain shape the performance of adapter tuning and domain adapter? And this table demonstrates our main results. And firstly, we can see that with appropriate backbone model, we can achieve great results with adapter tuning by tuning only a small number of parameters, specifically by comparing the results of each method with BioBird, which is in the first column for each method. We find that both the adapter tuning and domain adapter approaches achieve similar performances to that of fine tuning, and even outperforms it on the drug chemistry domain and the species domain for the adapter tuning and domain adapter respectively. And secondly, we find that domain adapter demonstrates competitive performance only when applied to a BioBird backbone, while fails drastically when applied to the BIRD backbone, which can be shown here. So this indicates that the design choice of the backbone is very important for its performance. And thirdly, in the gene, protein, and drug chemistry and disease domains, we can see that the adapter tuning approaches actually outperforms a domain adapter. But for the species domain, a domain adapter outperforms adapter tuning. And since the first three domains have more data than the last one, we assume this is due to the difference in dataset sizes. A domain adapter approach is more preferable when the training data is limited. This is reasonable since domain adapter can better utilize the domain prior, which makes up for the lack of training data to some extent. And in this experiment, we compare different design choices of adapters. Their structures are illustrated in the figure. And from the table, we observe that the parallel config shows dominant performance over the sequential counterparts across majority of the tasks, which indicates that the parallel config is a more preferable design choice. And in this section, we compare the adapter tuning method with prefix tuning counterpart. Specifically, prefix tuning attaches some tunable parameters before the key and values of the multi-head attention in each layer. And we conduct experiments over 4 different domains and compare their results and observe that adapter tuning demonstrates dominant performance over prefix tuning across all the tasks. And thank you. This is all for our presentation.